series final talk about algebraic structures of Steinberg modules, of algebras.
Yeah. Okay, so we're going to talk about Hopf algebra structures on Steinberg modules and applications to homology arithmetic groups. So in particular, GLN, SLN, congruent subgroups. R will be a PID, F is a field, K, they are a coefficient ring, often Q. Okay, so I'll just remind you what, I think today I'm actually just going to say bialgebras most of the time instead of Hopf algebras, but, so I'll remind you what a bialgebra is. So, new A tensor A to A. There's a co-multiplication. Delta A tensor A. And the important diagram that they need to satisfy, you start with A tensor A, and you can multiply, you get to A, you can co-multiply, you get back to A tensor A, and that should be the same thing as you co-multiply 4 copies of A. Then you swap these two factors. And then you multiply these two and these two. You get back here, and this diagram is required to commute. Okay, so why do we care about bialgebras? Well, there's this theorem of Leray that says if A is a connected bialgebra, connected graded and graded bialgebra. Because we need graded to make sense of connected over Q. Then, as a ring, A is free. So it's isomorphic to sim. Is a commutative. Then as a ring, A is isomorphic to sim of Q. So in particular, it's free. And most of the corollaries that I'm going to present in this talk, or like this, at least a sample of it, is the following theorem, independently established by Abner Ash, myself, and Peter, and Brown, Chang, Sorglatius, and Champagne. It's the homology of general linear groups with Steinberg coefficients. This is just the sum over n of the homology of the GLNs. Steinberg coefficients is a connected by algebra. So in particular, it's free.
So here this is GLN R.
GLN. Yeah, so I think we stated for PIDs, they stated for Dedekind domains.
They stated for Z.
In person, they stated for Dedekind domains.
In person, I stated for Dedekind domains too.
Our paper says PID. I don't know. I don't read, but I've heard Soren say Dedekind domain. I guess technically.
If you say Dedekind domain, probably that's not the right statement.
Oh yeah, good point. Okay, so we'll just say PID. Because I said N. N is my symbol for projective. And I think probably technically we need field coefficients to like use Kunitz somewhere. Peter, didn't you tell me at this point?
Oh.
Or Tatiana told Peter, who told me. Okay. But like in particular, we don't need characteristic 0, and we don't need like GL of a field or something. Okay. So.
Jeremy?
Yeah.
Is there a version with a determinant?
Yeah, there's a version with a determinant.
We have any character. You can tensor with any character of R.
Yeah, I'll state that, and then the notes for my talk, I was going to say, and Eric told you about all of this, like amazing applications of this, but he ran out of time. But I also won't have time to mention your applications. But or I will mention I already mentioned they exist. So I'll mention again that they exist.
Thank you.
Yeah, but so basically the idea, or how this is useful, is if you can find stuff in here, then that'll generate a free graded commutative subring. So it's very easy to produce loads and loads of unstable cohomology classes in the homology of GLN. Okay, so yeah, but the goal of this talk is to tell you what is the story for the Steinberg modules themselves. Yeah, and then this result will be a shadow of what the structure of a structure that Steinberg modules have. Okay, so let's just review the product. So VB is finitely generated free R modules, and isomorphisms as morphisms. And so if you have M and N from VB to K modules, we have this day convolution tensor product. I'll say U plus W is V, MU, NB, and W, and Steinberg has a product with respect to day convolution given by if you have an apartment and another apartment, concatenate them. Okay. And here. Now, sort of the funny thing is that, so the theorem is going to be that Steinberg is a bialgebra. The funny thing is the coproduct uses a different monoidal structure on this category. So this is, people who are used to Hopf algebras, maybe they're not used to, they're probably used to using one monoidal structure for the product and the same one for the coproduct. But here we need to use a different one. Yeah, so the parabolic tensor product, again, M and N are VB modules, is given by now the sum of W contained in V. By this I mean a summand of M of W, and now we don't have a preferred complement, but we can still evaluate it on the quotient. Yeah, so this is a smaller indexing set because we don't have the data of a complement. And I guess concretely, this one, the day convolution can be described as induction, direct sum over A plus B equals N of inducing up from GLA across GLB to GLN MRA and RB. And here it's also induction, but involving a parabolic subgroup instead of this product. I guess I could write A plus B equals N or A less than or equal to N. Those are the same thing. But now what's different and let's write what do I want to call it? P GLN and and P is the parabolic of that form. Okay. Oh yeah, I guess. So this is a monoidal structure.
Second M, there's an N, right?
This is A.
No, right next to it.
This is an N. Yeah, is that the issue?
What's the statement? This is for this specific.
Right now, it is nothing about Steinberg. I'm claiming that the category of VB modules has another monoidal structure, this time not symmetric, given by this formula.
Yeah, sorry, but what's the relation between the first and the second row?
This is supposed to just be a decategorified version of the other row.
If you plug in V,
I'm just a bit confused because above there seems to be over all W's, whereas at the bottom you would only take the ones that are embedded in a certain way.
But the induction gives you all the other ones.
Okay, yeah, okay. Sorry, yeah, thanks.
Yeah. It's supposed to just be like making that more concrete, but.
We're going to make a minor objection to the terminology,
Yeah.
which is that P guy is also deconvolution, but for a promonoidal structure on vector spaces. So I don't really like calling this guy deconvolution if that guy is also deconvolution, but for a different.
Yeah. Okay.
I mean, don't change it now, but just.
I could call it like Levy
Yeah.
or something, but That will probably confuse me. And then it has a shorter name, so maybe subscript L is better. Okay, yeah. So what does that do?
Night convolution.
So the coproduct uses this parabolic monoidal structure. So if we have V1 through Vn in Steinberg V, we send it to sum I less than or equal to n of shuffles pi sine pi I can't read my own notes. So this is in Steinberg of the span of V pi 1. This is in Steinberg. Yeah. So this is given by merging two apartments, and this is given by splitting apartments. This formula, as written, literally makes sense if you replace this with day, because we have this gives us a canonical, we have a basis, so we have a canonical choice of complement. But if you check, is it well defined, the answer is going to be no, unless you use, unless you, I guess I should, then you should object, then I should say this is V mod that.
No, not that, not the first one.
Well, the first one is one. Yes. So the formula maybe looks like you could just use day convolution, but it doesn't work out. Yeah. So then, the sort of VB version of the theorem I just erased is the observation that Steinberg first I'll say Steinberg is a coalgebra in mod VB B. And yeah, so we want to say, so it's an algebra and it's a coalgebra. So now I'm going to tell you what compatibility you need on two different monoidal structures to make sense of algebras. So the relevant framework is duoidal categories, which Oscar found the name on NLab. I don't know. There are other names, I think, but they're less fun. Like, I don't know. So a duoidal category is a category with two duoidal structures. And the key thing is there's an interchange. So the interchange gives you morphisms and tensor M, other tensor O, first tensor P, 2 and tensor O, such that, you know, lots of diagrams. Mute. So the, you know, when I wrote out the definition of a bialgebra, there was this swap, and it's going to turn out that the bialgebra, in this duoidal sense, the swap will involve the interchange. So. What's the diagram for a bialgebra look like in this duoidal sense?
So, what's the condition on the monoidal unit? Or is there no condition?
I don't know. Oh yeah. So I mean the example of the duoidal category is going to be VB modules, parabolic, and day. There's a chance I wrote them in the wrong order, because you know the interchange goes one particular way. So yeah. We'll find out.
Yeah, you wrote them in the wrong order.
I wrote them in the wrong order.
Specify the order, so you're fine.
No, no.
Like there's this order, like then there's an interchange. So if this order is supposed to be the same as this order, then I could be wrong.
Then you are wrong.
Peter says I am wrong.
Let's just switch those two.
And then people can offer other opinions. I trust Peter, but we'll see. Okay, so what we want to say a bialgebra is, in this duoidal sense, a duoidal bialgebra is, well, we have an algebra. Peter can then tell me that that now there's no. Do you want to stop? I'm good? Good here, okay. That was a chance. Okay, probably the diagram I haven't flipped, square and circle tensor. Okay, we start out like this.
Yeah.
We start out like this. So circle tensor, we know how to multiply. We get to A, and then delta we co-multiply, and now, I should have done the bottom row because that's, put it up here. Okay, so now we do co-product. It's bad. Oh. No, it's good notation, right? It's tensor co-product, and we get A square, A circle, A square A, and then we do the interchange.
Put brackets around.
Yeah.
That square isn't very nice looking, but square. Yeah, so in addition to, before we just swap these two things, but now we've swapped the circles and the squares. And now we do mu square tensor mu, and we end up here. And we're asking that this commutes. Okay, and the claim.
So,
Yeah.
if tensor and square tensor are the same, this seems like it's not the same as what you had before because you were lacking the swap, right?
No,
The integral has a swap.
Oh, I see. Oh,
And O.
turns around. Yeah, yeah.
Oh, yeah.
Okay.
Okay, so yeah, so Steinberg itself is a bialgebra. Now in this monoidal sense with respect to these two monoidal structures on VB modules. So
Secretly, there's also a unit and a co-unit, but we're not talking.
yeah, that's part of the data, and I didn't. Yeah, I guess I acted like dot 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 was just things commute, but there's that extra structure that, yeah, I'm not mentioning. I agree. Oh yeah, so it's connected, so you might hope that it's free, but unfortunately that's not the case. So we don't have a duoidal Laray's theorem for VB modules. So Steinberg is commutative and connected, but not free. You know, everyone will always say, you know, it's a good exercise on the hike or something. This Q Steinberg is the trivial representation of GL1 and then 0 everywhere else. And this thing is basically the formula for the Steinberg module, but it's missing the Boykowski relations. So Boykowski relations are non-zero relations, so these two things are different. Yeah. Okay. So, oh yeah, maybe I'll just say it in words. Co-algebras are always.
Is this last remark literally true? Is Steinberg actually commutative the way you've defined it?
Graded commutative.
Oh, it would,
It's a yes/no question.
unless I'm missing some subtlety.
You didn't define what
the answer is yes, but it
Depends
depends on how you define commutative.
No, it doesn't, because you don't get to choose what commutative means. If you're in a symmetric monoidal category, commutative has a meaning.
Yeah.
Yeah,
Graded commutative.
but it depends on the choice of symmetric monoidal category, right? Depends on the twist map you choose.
You worried about signs, or what are you?
Yes.
Oh.
You-
Yeah, I guess I should say it's instead of Steinberg going to K modules, it should go to graded K modules, and it should be in a grading where where you want to call it commutative instead of
Yeah, okay.
but yeah, I guess
It's graded commutative.
it's graded commutative, and I in the Larray theorem also ignored that subtlety there too. But yeah, but I mean, I think this is an indication that this sim is in a graded sense also. So it's I don't think we should believe there's hope for a Larray theorem. But
There is a surjection from this to Steinberg.
yeah, there's
So in particular, something commutative has this as a quotient, so it's commutative in that same sense.
yeah.
Jeremy, if I did E1 Steinberg, which presumably has a product and a co-product for just the day convolutions mathematical structure, would that be free?
Say that again?
He's asking, is Steinberg E1 free because it's a bialgebra in a.
So I thought that at some point, and I might have communicated that to you at some point, but I don't think that anymore.
Yeah.
The array does not seem to hold even for monoidal Hopf algebras.
However, we think that for monoidal Hopf algebras in great generality, we still have a fundamental theorem of Hopf modules, but we're not completely sure. But we think we don't have Leray in great generality, but we do have a fundamental theorem of Hopf modules. But yeah, we should learn this stuff better. Oh yeah, I was going to say, I wrote down an explicit formula for the product and the coproduct. At least the coproduct has some categorical meaning. There's a way of interpreting at least the homotopy type of the Steinberg module as a bar construction with respect to this parabolic induction. That if you take the underlying VB module and take parabolic bar on it, you get something that looks like or that is basically chains on the Tietz building. And the expectation, so bar constructions have a natural coalgebra structure. The expectation is that's the same as what I wrote down here. I think maybe you guys have shown that.
Yeah, we think we'll need this, so we have.
Okay. Yes. They will have written that down.
So just to clarify, so what's going on is that the Leray theorem holds for graded modules and it doesn't hold for VB modules? That's why it's failing?
Yeah, but then Sanders' question was, is the issue VB or is the issue that it's duoidal? And we think maybe it's just the issue is that it's VB, that even if you had used the day convolution in both situations, it would still fail, but we're less,
Two issues.
we haven't checked that example as carefully as, this definitely isn't free. Okay, so. Some implications for homology of GLNZ and SLNZ. Yeah, so I'll just R Z, and I'm going to take the coefficients to be Q, even though I won't write that. So homology of SLNZ is isomorphic to the homology of GLNZ plus the homology, and some writing cohomology of GLNZ with determinant coefficients. And Borel-Serre duality tells us, most people state it for SLNZ, but I'll state it for GLNZ. So it says the codimension I cohomology with trivial coefficients is isomorphic to the homology with Steinberg coefficients if n is odd, and the homology with Steinberg tensor determinant if n is even. So Steinberg is not the dualizing module for GLN. When n is even, you have to tensor with the determinant representation. This is for Z. For other numberings, it's more complicated.
It might be. Oh yeah, you said KQ. Okay, sorry. Emphasize K. You need that K is.
Yeah. And I guess this one is wrong when n is 0. If you also want to object to things. Yeah. And so these two things these two equations tell us that the homology of GLN and the homology of SLN are completely determined by the homology of GLN with Steinberg coefficients and the homology of GLN with Steinberg tensor determinant coefficients. Leave the n equals 0 so exercise. Yeah, and this observation that Steinberg is a duoidal bialgebra has the corollary that the homology of GL with coefficients in Steinberg and the homology of GL with coefficients in Steinberg tensor determinant are bialgebras. So the homology of SLN isn't a Hopf algebra, but it's this direct sum of two Hopf algebras with their unit glued together. Okay, and there are lots of corollaries that I was hoping Eric would tell us about, where, you know, his group and also the Brown, Chan, Galatius Payne group construct lots of indecomposable classes and hence lots of unstable classes. I'm going to tell you about the sort of dumbest possible way of producing new cohomology classes. Yeah, oh, out of time, whatever. But it's still interesting. So, okay, so the Tn, so I'm not going to talk about congruent subgroups at all today, I guess. Tn is the, is going to be the generator well, you look at the n choose 2 homology of GLN with Steinberg coefficients. This is isomorphic to H0 GLN is isomorphic to Q. So this is for n odd. Let Tn be the generator of this group that's isomorphic to Q. Z. GLN, coefficient Steinberg n, tensor determinant. So when n is even, this is isomorphic to this, when n is even, and when n is odd, it's isomorphic to this. So this group is Q. Pick any generator you want, or maybe the unit for the cup product. So Tn is non-zero, and if that Tn is non-zero in the indecomposables, whichever group it lives in, basically for degree reasons. So there are no non-trivial products can land in either group. So in this grading, indecomposables are just isomorphic to the group before modding out by products. So that tells you that these things are non-zero. But the existence of these classes is enough to show the homological stability, stable range of least one is sharp, and to show that you can't possibly improve the Church-Farr-Putman vanishing conjecture. Yeah, so we're looking at the homology of cohomology of SL. Let's say HI SLN. this is I, this is N, and we have this range, this quadratic range, above which the homology is 0, and then we have this linear range, maybe n minus 2, and below it it's stable. Yeah, so this is the theorem of Borel, and the current range is Sun and Lee. And then there's this conjectural range, where if you are in fixed codimension, you're also conjecturally 0. This is the Church-Farr-Putman stable range. And using these classes, you can see that so you can't improve the Church-Farr-Putman conjecture, so it might not be true, but nothing stronger than that is true. And also the Borel or the Sun-Lee stable range can't be improved. So T2n minus 1 times T1 is in the homology of GL 2n with determinant coefficients. It's not equal to 0 in here. So you can think of this as a subgroup of the homology of SL2n, and the image of the stabilization map.
Other way around.
Other way around.
Yeah, because it's called.
Oh, it's cohomology. What am I saying?
It's a sub-module, it doesn't contain it.
Yeah. So. Yeah. That is what I want. There's a typo in my notes. Okay, great. That is obviously what I want. Yeah. So these give you classes in here, and then everything that comes from the stabilization map factors through the homology with trivial coefficients. So these classes are not in the image of the stabilization map. So these classes show that this stable range can't be improved. And then similarly, Church-Farr-Putman conjecture in general can't be improved. So this is a theorem of Ash, independently in some cases of ground, that says these groups are non-zero for n equals 1 mod 3 and bigger than or equal to 4. And the proof, in some sense, is T3 to the n times T1 is not equal to 0. Yeah, so any product of indecomposables is not 0 unless it's 0 for sign reasons. And these classes live in this group, so we get this range can't be improved. This range can't be improved. I don't have time to talk about congruent subgroups.
You still have 5 minutes.
I started 5 minutes late. Maybe I'll say something.
Brown would that be?
What?
Which Brown would that be?
Francis?
Oh, not Kenneth.
Yeah. No, this is like
Recent.
recent. yeah, I guess even though, you know, Avner has been around for a while, this is,
Say like how I group now or something like
What?
there, like for this range.
what? Oh, yeah.
I forget the quarter.
Oh, yeah.
And
Yeah. Oh, yeah. This like maybe is independent work of Gerbach and Grobner.
Sorry, which is? Which result?
That this range is sharp. Maybe other people. They sent us a preprint that I think didn't say this was sharp, and then like we emailed them this argument, and then they wrote up a different argument. And it's like not on the archive; it's just on their website. I don't know. We're not going to fight them for. And maybe someone else knew this earlier. Okay. Yeah, I mean, so maybe I'll just state a theorem of an Abner-Ash. So yeah, these results are recent, but there's a theorem of Abner-Ash from the 90s that says that the map from a congruent subgroup with Steinberg coefficients, tensor yeah, so there's a block sum map on congruent subgroups of this form, and Abner-Ash proved it's injective. And his proof, he didn't know things were Hopf algebras, but basically he multiplied things, and then he co-multiplied, and got what he started with, roughly. This is 30 years ago or whatever. We work in progress with Peter, myself, and Avner. So this map extends to a direct sum of splittings of n plus m into subspaces, or splittings of roughly z mod L to the n plus m into subspaces. So there's a lot more multiplication maps of this form. So you can direct sum over all of them, ask if that's injective. It's not, but there's going to be a large subset of other multiplication maps. So, you know, this lets you produce unstable classes, but I don't know, you know, we don't quite think we have the right statement, but you can improve this result and get a recipe for constructing lots of unstable classes and congruent subgroups as well. That's all I have time to say.
questions?
One question to multiple speakers probably. So we saw a couple of algebraic structures on computing or almost computing homology of SLN or GLN. And so my question as an operatic person is, so what's the totality of the algebraic structures on BGL or BSL? So what's the operand acting? Because you see, for example, I don't know, in Oscar's talk we saw there's an infinity structure. I think that is not debatable, but the infinity structure does not give you the Hopf algebra structure, right? That you
I've been saying commutative whenever Oscar says E infinity, but yeah, I mean, this is, I mean, I guess there's also, Oscar's talk was just about infinite fields, so there, with this Suslin-Nesterenko business, homology of GLN is closely related to the homology of GLN with Steinberg coefficients. Here, because I was thinking about number rings like the integers, then the connection between the homology of GLN and Steinberg modules is very different. It was via Borel-Serre duality. Yeah, I mean, I don't know about. So in some sense, like if you were to apply this to GLN of some ring that's not an infinite field and not a number ring, then this is only a theorem about homology of GLN with twisted coefficients and doesn't tell you anything about, or doesn't immediately tell you anything about the homology of GLN with untwisted coefficients. Yeah, I don't really have a good answer other than like we continue to find new structures that seem to have concrete consequences, but I don't know anything more.
Yeah, I mean, there's a product, there's a coproduct, there's also a cup product, there's a Pontryagin product, there's, yeah, I mean, I guess the product.
I think we're talking about different groups in different cases, and now we should say which group we're talking about when we're talking about different algebraic structures. If we just list all algebraic structures that exist in all possible different groups you could consider, that gets very confusing. So maybe just make a table and during the break about what exists.
If you want to connect back to stuff from previous days, the indecomposables, if is the same thing as homology of GLN with Steinberg-Lie coefficients for, So, these T's are, elements of homology of GLN with Steinberg-Lie coefficients for suitable definition of Steinberg-Lie. Yeah.
Something you, maybe I missed it, but you didn't comment on how, when you take homology to go to homology of GLN Steinberg, the two monoidal structures become apparently the same.
Oh,
so
yeah, yes.
Talk about.
Yeah, I should have said, yeah, so, yeah, the reason why, somehow, up to the action of GLN, there's only one way of splitting it into a subspace of size A and a subspace of size B, and there's only one way of finding a subspace of size, a summand of size V. So they become the same monoidal structure. That's not everything, but
if you have the parabolic monoidal structure and you take homology, then by Shapiro you get homology in the parabolic subgroup. But the parabolic subgroup acts on the coefficients via the projection to the levy, and then you just project to the levy, and then you need what we said earlier. What's the word when you?
Shapiro's lemma?
No, not the tensor product thing in cohomology. König. Something with K is like Kazoo, no, König. König to get to actual, but you need a map. It's not just, it doesn't just go into, doesn't just turn into that.
But yeah, you also need that you were talking about the stabilizers. You also need the orbits are the same. Right. What I said was the orbits are the same. So yeah.
Yeah, let's thank Jeremy again.